everybody. I'm going to just kick us off. So today I'm going to be talking to you about CSS, but not just, I would say not really just using CSS and writing CSS, but how to debug your CSS. So I don't know how many of people have heard this quote, but a language that doesn't affect the way you think about programming is not worth knowing. I know a lot of people, there's a lot of conversation sometimes on Twitter about whether or not CSS is a programming language, but technically it is a markup language. But I would argue it does affect the way we think about programming, whether that is saying cuss words to ourselves. It definitely affects the way that we think about things. And I think sometimes we will approach CSS with the same mindset as we do our JavaScript or other programming languages, but a lot of times it's very different. And then there's this GIF. It's probably the most famous CSS GIF. So I don't know how many people feel like this, but I have definitely felt like this, whether I was implementing my own CSS from scratch or debugging someone else's CSS. And then there's this as well. This is another famous one about CSS. People like to argue that it can't kill you. I would still argue that it can't, but this is still pretty funny. So a little bit about me before we get started. When I wrote this talk, I was specifically a front-end engineer at Warner Brothers, and it was in that role that I realized that I didn't really know CSS all that well. I felt really confident when it came to debugging my JavaScript, but when it came to more advanced CSS, I really felt like I was blindly throwing darts at a dartboard. I am currently a DevOps engineer, so I've made a little bit of a switch, but I still really nerd out on the internals of browsers and things like that. I am a panelist on the JavaScript Driver podcast, and I know Dan Shapiro, who also works at Wix. He is one of my one of the panelists along with me. I used to be a competitive figure skater. I spent a lot of time working out. I have 2 cats and drink a lot of hot tea. So that's a little bit about me. So as software developers, we spend more time usually reading than writing source code. And I think knowledge of internals can be useful for advanced debugging and also for performance tuning. And the other reason why I think understanding the internals of CSS are really important is because we're now able to modify the browser's rendering engine ourselves. And that's with something called Houdini. Normally, if this was an in-person talk, I would kind of gauge the room and see who's heard of Houdini. Hopefully, more and more people are becoming aware of it. But it's basically, it has a lot of different features. A couple of those are that it allows you to normalize cross-browser differences, which is becoming less and less nowadays, but still very important. And then it'll allow you to invent or polyfill new features. So we can kind of think of it as Babel or TypeScript or something like that for our CSS. So, and a lot of people ask, you know, is Houdini ready yet? This is a website that you can go to. It's just ishoudinireadyyet.com. But you can see that a lot of the things like the layout API, the paint API, most modern browsers are shipping with that now. So it is definitely ready for you guys to play with it. And then finally, why I think that this is important is just low-level programming is good for the programmer's soul. So one of the most common questions I get, especially from JavaScript developers, and you know whether or not they really need to take the time to deep dive into CSS, is can't I just use component-based styling? Doesn't that just magically fix all my CSS issues? Or I'll just write JavaScript instead. So the thing with component-based styling is you gain specificity, but you lose the cascade. And that's really like a core feature of CSS. And it's something that you want to embrace, not run away from, I think. So a couple of the other issues, you're no longer able to change one variable to update all the colors like you would with the cascade. You're unable to affect child classes by their parent. And then the browser has a lot of built-in optimizations for CSS that if you're writing JavaScript that you're not going to get. So this talk is going to be segmented into 3 different parts. We're going to get into browser internals, the parsing process, and then the common issues that I hear from developers the most. So a little bit of vocabulary to get us started, because I think sometimes even more advanced developers don't even necessarily know the differences. So we have the browser itself, which you would have like Chrome, which is based on Chromium, and then you have the rendering engine, and then you have the JavaScript engine. So the rendering engine is responsible for our HTML and CSS, as in the JavaScript engine is only responsible for the JavaScript, obviously. So how do browsers actually work? Here's a little bit of a diagram. So you have the user interface layer, which interacts with the browser engine, which interacts with the rendering engine. The rendering engine is where we'll spend most of our time on today. You also have a networking layer. You have a UI backend and a data persistence layer. So the rendering engine is going to go through a specific flow, and that's what this looks like. And we're going to break up each piece carefully. So first, we're going to start off at the DOM, which most people are probably familiar with from their JavaScript. And how that works is the HTML parser is going to start, and it receives these raw bytes, and from there we're broken up into 2 different phases, the tokenization phase and the tree construction phase. So we start off with these raw bytes. You can kind of visualize what that would look like here. So definitely not what we would expect if we're just inspecting source. And the process of going from these raw bytes to the next step is called conversion. From there, we have the individual character code. So those raw bytes are translated into these individual character codes based on the file encoding. From there, the individual characters are broken up into tokens via the tokenizer. So what the tokenizer does, it's going to break up that input into valid tokens. So we can think of, if we're parsing the DOM, things like the start tag, end tag, attribute names, attribute values, and it's smart enough to strip irrelevant characters like white space and line breaks. And this is often combined with something called lexing, but they're basically the same thing. So we can imagine the tokenizer output is something like this. Next, from the tokenizer, we break up everything into these individual nodes that we can think of are basically like objects. That's done via the parser. So it's going to read the stream of tokens, analyze the document structure according to the language grammar. And what I mean by that is the language grammar is represented by the vocabulary and syntax rules for that language. And then finally, we get to what we're probably most familiar with. This is the DOM structure, and that's done via the compiler. It parses the source code into this tree structure that we're familiar with. So one thing to understand about the DOM and why it's quite different from CSS. So when people talk about the DOM, they'll often say it's not context-free. And if we think about it, so browsers are made to be able to render ill-formed HTML. So when the browser is rendering the DOM, it has to be smart enough to take into account like what comes before, what comes after. That's what we mean by context, because the browser is smart enough. If you forget to close a tag, then the browser actually has code within it to close that tag for you, which is very different from CSS. So I kind of imagine if I'm inside the browser and someone hands me and I'm the browser and I'm given some ill-formed HTML, I'm probably going to be reading that HTML a little bit like this. It's basically an unconventional parser. Whereas with CSS is a conventional parser. So hopefully it's a lot more smooth. So to recap the DOM before we move on to the CSS object model. So the browser sends an HTTP request for the page. The web server sends back the response. The browser then converts those raw data bytes into tokens via the tokenizer. The browser is then going to turn those tokens into nodes. The browser then turns those nodes into the DOM tree that we're familiar with. Once the DOM tree construction is finished, then we can go on to the CSS object model construction. And at this point, everything pauses as well as it's rendering things by default until the CSS is constructed. So I don't know about y'all, but the first time that I was really digging into this stuff and trying to understand my CSS, I had never heard of the CSS or the CSS object model. And so I'm going to go through the process of that, which is very similar to HTML, but it is a little bit different. But yeah, I had definitely never heard of it before. It's important to understand, though, that the DOM and the CSS are completely independent data structures to the browser. But we can think of it very similar to as we're parsing HTML or JavaScript. It's fairly similar to an abstract syntax tree like you would have in JavaScript, just this tree structure. Like HTML, we need to convert the CSS rules into something the browser can actually understand. So the process that we went through for HTML, we're going to repeat that same process for CSS. By default, CSS is treated as a render blocking resource. And the browser is going to hold off rendering of any process until the CSS is constructed. So the first thing that happens, you can imagine, is the browser encounters a link tag in the head of your style sheet, and it's going to dispatch a request for that, and everything stops. Scripts asking for style information during the document parsing, if the style is not loaded and parsed, that would mean that the script is going to get wrong answers. So that's why it's important that everything stops. And this is also incremental, and that's because of the cascade. You could imagine if something higher up in the tree was giving it a color red and something lower down was giving it a color blue, that would be really jarring for the user. So again, we go through the same process. The CSS files are parsed into style sheet objects. Each style sheet object contains a CSS rules object. Each rules object contains selector and declaration objects, and then other objects corresponding to the CSS grammar. So if we want to visualize that, to compute the final styles for the object on the page, the browser starts with the most general rule for a node, which would be the body element, and then it recursively computes the styles by applying more and more specific rules via the cascade. But as I mentioned earlier, it is really important to keep in mind that the CSS object model is not one-to-one with the DOM. And hopefully as I go on, this will make more sense. So things like display none, script tags, meta tags, head elements, those are omitted from the CSS object model because they're not reflected in the rendered output. So the DOM tree captures properties and relationships to the document markup, but it doesn't tell how the element should look once it's rendered. That's the responsibility of the CSS object model. One difference between display none and visibility hidden that's important to understand is visibility hidden will appear in the CSS object model, whereas display none won't. So we finally have the DOM tree constructed and the CSS object model constructed. Then we take that, we mash them together, and we have something called the render tree. So you can visualize it a little bit like this. It's a tree of visual elements in the order in which they're going to be displayed to the page. So what is the rendered tree, though? So we have a pretty good understanding now of what the DOM is, what the CSS is. So the rendered tree, as I said, is a visual representation of the document. It enables painting of the contents on the page in their correct order. And it's important to know the CSS object model can have drastic effects on the rendered tree, but again, because they're independent data structures, it doesn't have any effect whatsoever on the DOM tree. One thing to keep in mind too, why we need to have this render tree is because the CSS object model, as we know, it can with our CSS, we can reorder nodes in the DOM. So the purpose of the render tree, it knows how to lay out and paint itself and recursively its children. It's going to include geometric information like width, height, and position. And then each node in the DOM tree that produces visual output has a corresponding render object in the render tree. So hopefully that helps everyone visualize this stuff pretty well. So how is the render tree constructed? So starting at the root of the DOM, we traverse each node. We're going to omit the non-visible nodes, so things like the meta tags. For each visible node, we find the matching CSS object model rule and apply that. Omit the visible nodes with the content and computed styles together. And then that outputs the render tree that contains both the content and style information of all the visible content that the user will see on the screen. Okay, so on to the second portion of this talk, now that we know kind of how this process goes to get to the render tree. Once we have the CSS object model and the DOM, we're going to go through layout, paint, and composite. Those are phases within the browser. So back to the original diagram, you can imagine that we are now here. So just like with our JavaScript, you can investigate and debug how long the layout process is taking by going to the Performance tab. A lot of times, if you're talking to people who work on the browsers themselves, they'll talk about layout as reflow. And that is calculating the position and size of the tree's render objects. And the output of the layout process is the box model that we're probably familiar with from CSS, and that contains the position and size of every element that we have in the viewport. After we go through layout, then we go through paint. Again, just like we did with layout, you can inspect how long this is taking as well, just like you would if you're trying to debug your JavaScript. Paint is often called raster sizing as well, and it's converting each node in the render tree to actual pixels on the screen. So how does the painting process work? We go through multiple rounds of painting, and that can be caused by JavaScript being loaded that changes the DOM. And it is going to include not things like size, but things like text colors, shadows, background images. And it's important to know that changing any property besides using a transform or opacity will always trigger a paint. And I'll get into a little bit later why this is important when we're actually thinking of the performance of our CSS. So painting time, it's going to vary based on the render tree construction. That makes sense. The bigger the width and height of the element, the longer it's going to take to paint to the screen. Adding different effects can also increase the painting time. And here's the part that I wanted to start pointing out performance-wise. So painting is usually the most expensive component of the render pipeline. And if we want to debug how long things are painting, the easiest thing to look at and the most sensible thing to look at first would just be the size of the area of the element. And here's something that I like to point out, because I know as JavaScript developers, we're sometimes more excited to learn new features in the JavaScript language than we are the CSS spec. So one thing to keep in mind, someone did an experiment and they had a floated layout and they converted that to Flexbox, and it went from, the speed went from 14 milliseconds to only 3.5 milliseconds. So I love Flexbox just from a usability standpoint, but it helps too with keeping our pages performant. So painting order, it's going to follow the order of the elements as they are in their stacking context. And I'll get into stacking context a little bit later as well when we're talking about the most common problems that people hit. And it's painted from back to front, and it can be global or incremental. And what I mean by that is you can see here that it is only affecting that small portion of the page. I'm not having to repaint the entire layout. because a render object, it's smart enough to know when it becomes invalid or has like a dirty region, and it only generates the paint event there. Finally, we're going to move on to composite. So you do sometimes, if you want to get a little bit deeper into debugging composite, I had to install an extra add-on to Chrome, but you can also debug the composite layer. What is composite? I know that this is not really so much new to browsers anymore, but it was a couple years ago. And what we mean by compositing is we're really talking about, if you've heard people talk about hardware acceleration. So we're using the GPU to speed up the rendering process versus the CPU. And we can cache and group chunks of the render tree together so that the painted parts are all painted to the screen as one. But again, going back to sometimes why it pays to keep up to your CSS with your CSS skills and not just use JavaScript for anything. With JavaScript, we're going to use the CPU. We're not going to be able to use the GPU. So rendering different elements of a page in different layers, we can think about Photoshop layers, and it's the action of flattening all the layers into a final image that's visible on the screen. So to take a step back and talk about performance here and why we need to understand these different phases in the browser. So changes to the element's position will cause a relayout and repaint of that element, its children, and possibly siblings. If we think about it, that's probably going to cost us performance-wise. Adding a DOM node is going to cause a relayout and repaint of the parent node. That's also probably going to cost us. Major changes like increasing the font size of the HTML element is going to cause a relayout and repaint of the entire tree. That's going to be pretty heavy. Changes to an element's color. If we're only changing the color with CSS, then we only have to trigger a paint and composite. But here's where, again, keeping up on our CSS skills and using more advanced features like transform and opacity, those only trigger composite. So whenever possible, that's what you would want to use because that's going to be most performant for your CSS. So to summarize the second section before we go on to the third section. The browser is smart enough to try to do the minimal possible actions in response to a change in our CSS. Layout is always going to trigger a paint since changing the geometry of an element means changing the pixels and those will need to be fixed. And then a paint is going to trigger a composite as well. So now to get on to a little bit of the more practical side of things and get away from the philosophical side. I don't know how other people feel, but this is often how I felt when I was writing CSS. And just all the different global things that can affect each other when you delete a block of code that you thought was useless. So I also have heard the analogy before that CSS is much like a bunch of toys floating in a bathtub, and you move one, and because of the water, all the others move around with it. It's not at all like our JavaScript where we're used to keeping things independent and a lot of times immutable. And then there's this, and this is probably like the main reason why I wrote this talk. I think there is like the stigma around CSS and people don't really want to learn it. And that's definitely the route that I fell into initially. When I was a brand new developer, I thought, CSS was easy. It was a markup language similar to HTML. And, it was really just like a matter of memorizing the different properties and rules. And I thought, JavaScript was the scary part. However, as I got further on into my career, I felt more confident writing JavaScript and being able to debug that. And CSS started to become the confusing part to me because I really didn't understand, aside from just applying certain styles, what was happening under the hood. And then there's this, people like to joke that CSS is just magic. As a software developer, I'll joke about that, but I actually think that mindset is really bad. We want to know why something is happening, why something's behaving the way it is, and not just guess. And we want a way to systematically debug our code and not just kind of blindly throw darts at a dartboard. We want to be able to rule out what may and may not be happening. So we're not just guessing. So the first thing, when I polled a bunch of people who write a lot of CSS and JavaScript, what they thought that they got tripped up on the most was specificity. So we're going to talk about that first, as far as the practical things that we need to debug in our CSS. So at a base level, specificity makes sense. There's a lot of ways to target a specific tag using different selectors, and it's just applying rules in the correct cascade order. If multiple selectors are targeting the same set of HTML elements, and if the CSS selectors are trying to assign the same property or properties to those HTML elements, then it sounds simple enough. The selector with the highest specificity value will win. And that's because the browser needs a smart way to negotiate which style rules should apply to a tag. The browser is going to make a decision by first calculating each selector's specificity value. And then second, it's going to check which selector is the highest value to determine the winner. So again, this sounds very simple, but it's pretty common, I think, for people to not understand how that calculation actually works. So we're going to talk about that next. So the first thing we need to do is we need to break apart these different types of selectors. So I'll have a little prerequisite before I have a quick quiz. So we have attribute selectors. Those are things like target equals blank, text type equals text. We have pseudo classes that people are probably familiar with, like hover or visited, and then pseudo elements. So things like before and after. The other thing that I don't have noted here, but we also have just plain old selectors, like we have an element like a div. So here's the quiz that I have. We have two divs nested inside of each other. One has a class, one has an ID. We have an href inside, and I want people to guess, and I'll give us, I actually do want people to guess. So I'm going to give us I'm going to pause for a minute or so and let people see if they can figure out the answers. Again, if we were in person, I wish that I could have people raising their hands. I don't have the chat open to see, but go ahead and take a guess. As we're waiting, I know from talking to different people like hiring managers and stuff, and I think I heard on a podcast once that this is a popular interview question at Netflix, or was. I'm watching the timer. I'll give you 20 more seconds. Okay, 5 more seconds. Okay. So the answer, this is probably how a lot of people are feeling right now. Whoops. The answer is blue. And if you didn't get that right, I'm going to explain why that is. So for specificity, we can read the values. We can read them as if they were a number. So if we had in our calculation 0, 1, 1, 1, we can think of it as 1, 1, 1. The commas are there, though, to remind us that it's not a base 10 system, so we do need to be a little bit careful. We can have a specificity value of something containing 13, and the 13 won't spill over like a base 10 system. So let's go over how that calculation works. So for the first one, we have a class of container. We have the ID of main and the anchor tag. Then we have the div. We have the ID of main and then 2 tags. Then we have the third one, the fourth one, and the fifth one. So let's talk about how these are calculated. A lot of times it helps to write this down on a piece of paper. So for A, we have the style attributes, and that's the first column. Those are going to be worth 1 point in that column. Then we count up the number of ID selectors. That's going to give us the number in our second column. So we can see how for the first 3 here, we have a 1 there. Then we're going to count up the number of class selectors. the number of attribute selectors and pseudo classes. That'll give us our third column. So we can see now why the top one is pulling ahead, because we do have one thing that we can count there. Then we're going to count up the number of type selectors. And what I mean by type selectors are just the individual nodes. So like in the second case, the second from the bottom, we have a p tag and an anchor tag. That's why we have 2 in that last column. In the second one, we have div, we have p tag and anchor tag. That's why I have 3 in the final column there. But again, to get to the end, we counted up each one, added those together, and that's why blue won. So just a recap here, we have 0 style attributes. So that's why we have 0 in the first column. We have 1 ID, which is the header. That's why we have 1 in column B. We have 1 class and 1 pseudo class. So we put 2 in column C. And then we have 2 type selectors, the LI and the A, and that's how we get the number in column D. So hopefully now we have a better way of actually calculating up how specificity is working if we need to systematically debug that. Next, I'm going to get into positioning. So positioning is the process of determining the position and size of all of the boxes on the page. So going back to the layout process that we were talking about in the render pipeline. And positioning typically sounds pretty simple, but as with most things, it's going to be a little bit more complicated than we think. We have normal, where the object is positioned according to its place in the document, its box type and dimensions. Relative, the browser is going to position it like usual, but then whatever value we give, the browser is going to move it by that number, that delta. So float, as we were talking about earlier, that we don't really want to use anymore, but I think it's important to understand how it works and why it was so tricky when we did have to use that instead of Flexbox. So with float, the object is first laid out in the normal flow, and then it's moved as far right or left as possible. For absolute, the object is put in the render tree in a completely different place than it would be in the DOM tree. So positioning is going to follow this phase or this series of phases. It's going to lay out in a recursive process where the width is computed by the current render object. The height is computed a little bit differently. So for each child, the current render object determines the position of the child, and it's going to ask the child to compute its dimensions. Then the current render object can compute its height. So if we've had issues where things are not the height we're expecting, but they're the width we're expecting, this is likely why. So if we want to visualize the width calculation, again, the parent tells the child to fit into its width. Okay, so we have global layout and incremental layout. With global layout, the layout can be triggered on the entire render tree as a result of a global style change that's going to affect all of the render objects. So that's going to cost us performance-wise. This is triggered synchronously. An example of this would be like changing the font size or the screen being resized. With incremental layout, as we were kind of seeing earlier where I was hovering over the button in the GIF, the browser is smart enough to know there are dirty render objects and only those need to be laid out. That's triggered asynchronously, so it's more performant. An example of this would be a new render object being appended to the render tree after extra content coming in from JavaScript script being loaded. Finally, I'm going to talk about ZIndex. I know for me, this was the most enlightening portion of the research I did for this talk because ZIndex definitely tripped me up a lot. It sounds simple at a base level, but again, there are a lot of things I think even with like very, very, very advanced front-end developers, I know for myself that I wasn't aware of. So for every element in an HTML document, it can be either in front or behind of every other element. And that's what we all understand at a base level how ZIndex works. And the elements with a higher Z-index are stacked in front of elements with a lower Z-index. But it's really that easy. It appears so simple, I think, on the surface that most developers don't really take the time to dive into it and understand it more thoroughly until they hit a pretty bad bug. So this is where we're going to explain, when we were talking about earlier, what stacking context is. And I think understanding stacking context is key to being able to debug your Z-index issues. Stacking context is a three-dimensional representation of the HTML elements along an imaginary Z-axis. So that would be like the person facing their screen. And it's an element that contains a set of layers. And we can think of stacking context as groups of elements with a common parent. And those groups of elements are going to move either backwards or forwards together. It's important to understand how stacking order works, though. Every stacking context has a single HTML element as its root element or its parent element. And when Z-index, and of course you need the position property there, aren't involved, the rules for stacking context are pretty simple. It's just the stacking order as it would appear in the order in the HTML. So for positioning, what I mean is you need to give something like relative or absolute, anything other than static, which is the default. So with stacking context, we have a couple of different types. We have the root stacking context, and that's created by the HTML element itself. We have a local stacking context, and that's created when we apply specific properties and values to a node. Within a local stacking context, the Z-index values of children are relative to the root element rather than to that HTML document root. Layers outside of a context, so sibling elements of a local stacking context, they can't sit between layers within another context. So what I mean by that is there needs to be a parent, and those siblings cannot affect each other. When a new stacking context is formed on an element, that stacking context confines all of its children to a particular place in its order. If an element is contained in a stacking context at the bottom of the stacking order, there's no way to get it in front or behind of another element in that context because they're all moving around together. So if we have different stacking, what I mean here is if we have different stacking contexts, no matter how high we give something a Z-index value of, it is not going to have an effect. It's all about understanding which stacking context you're in. So the rules for stacking context, for non-positioned elements, again, this is the simple part. We just check the stacking context root element, and we check the order of the appearance in the HTML. For positioned elements and their children, this is where it gets more complicated. Negative Z-index values, the higher values are stacked in front of the lower values. Elements with the same value are stacked according to just the order in the HTML. So back to the simple part. Negative Z-index values are ordered first within a stacking context, which means they appear behind all the other elements. Auto Z-index values, just ordered by their appearance in the HTML. Then we have the positive ones. This part is simple enough. The higher values are stacked in front of the lower values. And then elements with the same value, we go back to just the order of appearance in the HTML. I have a huge surprise, though, and this is where things get more complicated. And this was the part that was pretty enlightening for me. Z-index is not the only way to create a stacking context. So I know for me, a lot of times I did not realize this when I was debugging things, and it definitely made things very complicated. So the other ways that you can create stacking context with your CSS properties and values: opacity when it's anything less than 1, filter when its value is anything besides the default of none, mixed blend mode, anything besides the normal default, and transform values. So what I mean by that are things like scale and translate 3D. And just to kind of recap on these properties, since they're a little bit more advanced, blend mode is how the pixels interact with the pixel layers below it. Scale is going to affect the size of the element, and translate 3D is how we dip into the GPU transitions for a smoother experience in the browser. So summarizing this back up, when we need to debug ZIndex, we need to be able to spot when a new stacking context is formed. We need to be able to look up the ancestor tree and see if any parents form a new stacking context. And then there's this number. We have 2,147,483,647. That is the maximum number you can give your CSS, and that is because that's the max sign value of a 32-bit integer. So that is the limit placed upon us by the browser's programming language. So if you give it something higher than this, it will have 0 effect. And again, this was an extra extension that I added on to my browser. You can also debug ZIndex as well. So wrapping us up, in conclusion, we're going to go back through the different phases. So the first thing that the browser does when we need to render and parse our CSS, and why it's important to know this for debugging, we're going to construct the DOM by parsing the HTML, and that could be incremental, where a response may not arrive at once, so we may not finish the construction all at once. Then we start parsing that page. We come across our styles, and we're going to request the CSS and JavaScript resources if we have a script tag. If the scripts are synchronous, they're not going to be executed until the CSS is received, since CSS is render blocking. So that's the default. Then we complete the CSS object model construction to unblock the JavaScript engine. We execute the JavaScript. Finally, the browser is going to merge the DOM and the CSS object model together into the render tree. We run layout, paint, and composite. So I will leave you with this. I think computers are good at following your instructions, but not at reading our mind. And hopefully now you feel a little bit better about systematically debugging your CSS just like you would your JavaScript. Hopefully feeling a little less like this and a little more like this. Thank you.